All right, a couple more examples for you, and then we'll wrap up. Uh, we've got two series here, and we're going to again work through our variety of different tests to try to hone in on the right one. The nth term test is always where we want to start. And for the first case, it would be helpful to simplify here. And notice that the denominator can be written as, well, the numerator is just n to the 3/2. The denominator can be written as n to the 4th raised to the 1/2, which is just the same thing as n squared. And so ultimately, this is going to behave like 1 over n to the 1/2, which the limit as n goes to infinity of 1 over n to the 1/2 is 0. So that's not going to help us. Nth term is inconclusive. So next thing we might consider is geometric. Is it geometric? Well, we don't see a constant raised to the nth power. We have n raised to a constant power. It doesn't fit the format. It's not easy to see how we would write this as a telescoping series, given that there's really no difference between two terms, and it seems like it's about as simple as it's going to get. And so that's out. And we could try to use the integral test here, but in fact, this is actually one that we've already done the integral for. Because if you remember the p series, we actually showed that the sum of 1 over n to the p converges for p greater than 1, and it diverges for p less than or equal to 1. And in this case, we just have p equals 1/2. And so although it is an implication of the integral test, we don't need to redo the integral. We would say that this one diverges. It's the p series with p equals 1/2, which is less than or equal to 1. Okay, so once we've simplified that down, that's a much easier problem. The second problem, though, is going to take a little bit more work. So the nth term test is again going to be inconclusive, because the denominator goes to infinity, which makes this 0. It's not geometric, it's not telescoping, and the integral from 0 to infinity of 1 over root n to the 4th plus 1, that's a tricky integral. There may be a clever substitution that you could use there, but it's certainly not obvious what that would be. Okay? So I'm going to suggest that we, rather than trying to battle with that integral, we try a different approach. Let's try comparison. And for an appropriate choice for the comparison, we're going to have to think about, what do we think this series behaves like? And if we did not have that plus 1, notice this would be a much easier problem. Using the same sort of simplifications as the previous example, we would be able to write that as just a 1 over n squared. But given that we do have the plus 1, this is not equal to 1 over n squared. But it might be reasonable to hypothesize that it should behave like 1 over n squared. Since, again, if you ignore the plus 1, the root of n to the 4th is just n squared. All right? And we know that the sum of 1 over n squared converges. That's another p series. So we don't need to rework that problem. So if we can show that this does indeed behave like 1 over n squared, then we would be in great shape here. All right, and we could either go for the direct comparison test or the limit comparison test here. Let's try a limit comparison. So let's look at the limit as n goes to infinity of an over bn, which we can write as the limit as n goes to infinity of n squared over root n to the 4th plus 1. Still looks like we're going to have an indeterminate form there. If you plug in, you get infinity over infinity. And I don't really want to do L'Hopital's rule because the derivative of that denominator is going to be pretty ugly. So let's try to do some algebra. We'll multiply by, how about 1 over n squared on top and bottom? Although for the denominator, since we have a radical, it might be more convenient to write n squared as root n to the fourth. That's the same thing as n squared for positive values of n, but that'll make our simplification easier. So we'll have 1 on top, and then the bottom we'll have root n to the fourth plus 1 over n to the fourth, which is going to be 1 over root. That's a fraction that we could easily split up into two fractions. So it'll be n to the fourth over n to the fourth, which is 1, plus 1 over n to the fourth. And now it's clear that this approaches 1. And the limit comparison test says that if you get a constant that is positive, so L is greater than 0 and less than infinity, then that means that the two series must do the same thing. So the sum of AN converges because the sum of BN converges. All right, so I think we've covered all of the different tests in these example videos. I hope that the thought process that we've outlined here proves helpful for you for when you are trying to work out these problems on your own. One of the things you can do for practice is you can go to the chapter review section and just pick a generic series from there and try to apply the series test and identify the appropriate series tests without that context of, oh, it's in 10.3, therefore I know I should use a comparison. If you can do that consistently, then that's a sign that you're going to be very well prepared for some of the upcoming exams. All right. Now, before I close there, let me just throw out one more challenge problem for you. There are some series that are right on the edge of convergence and divergence, and it can be very difficult to tell whether they converge or diverge. Okay, so let me put a couple of series on the screen here for you to try on your own. I won't give you the answers now, but if you're curious, we can talk about these in office hours. But I would encourage you to actually try applying these tests to some of these problems. So here are some that you might want to consider. 1 over ln of n raised to the 3. The sum of 1 over n ln n. And we'll assume all of these are from n equals 2 to infinity, n equals 2 to infinity. Also, the sum of 1 over n times ln of n raised to the p, where p is some number. And why not? Let's do one more. Let's do the sum of ln of n over n to the p, where p is greater than 0 for both of these cases. All right, these are challenging series. Some of them may require comparison, some of them may require the integral test, some of them may require using the nth term test. Give them a try and see if you can figure these out for your own. And if you can't, definitely don't hesitate to ask about them through the forums or during office hours.